Hello and welcome to, here we go. Wait, hang on. Boop. Scheduled for, okay, yeah, we're good. All right, I almost said good morning. Good afternoon. Good afternoon and hey there from the disembodied voice that brings you chemistry about 3 times a week. This is our second Chem 400 first semester Gen Chem office hours that we are holding online, and this is also the last one before the impending exam, exam 2. So today we don't have a ton of questions, at least in the inbox email. Of course, we are totally down to take questions live as we go, but I'm gonna hit the questions that were emailed in first, and then I am more than happy to take any that come in live. All right, so jumping right in first, the first set of questions that we have here. First set of questions that we have are actually from the ACS homework assignment 5 and 6. Okay, here, hang on 1 second. I'm just gonna step out of the room and ask my kids to be a little quieter. I'll be back in 1 second. All right, apologies to everyone for that lag. There's a lot about this online education thing that's really I think interesting and cool and different, and but there definitely are some downsides. Like for example, I've never, right before I taught a class, had to clean up dog poop off the floor, which is what I was doing right before we started live streaming, because our dog thought it would be cool to add a little more chaos to the quarantine. So anyways, apologies for that lag. We have a question about the ACS homework. 3 different problems from the assignment for ACS 5 and 6. So this, if you're wondering, is coming from, this is coming from the first edition. So if you are working with the second edition of the book, the numbers or pages might be different. But the first one is problem 12 on page 50. All right, and the question reads, the standard enthalpy of formation for nitrogen 4 oxide, which is NO2, is the enthalpy change for which reaction? All right, so here is the question. They want to know the delta H of formation, or they want us to identify the change in enthalpy of formation for NO2. All right. Excuse me. And They want us. Sorry. They want us, yeah, basically to identify the formation reaction for NO2. The key thing to remember here in this problem is this F stands for delta H of formation. All right. And the definition of a formation reaction is a reaction that produces 1 mole of product from elements. All right, so there are many different reactions that make NO2. There are even several reactions that make NO2 as a sole product. However, the definition of a formation reaction is a reaction that produces 1 mole of NO2 from its constituent elements. So when you look at the elements that are in NO2, we've got nitrogen and we have oxygen. So elemental nitrogen, we're looking for a reaction that reacts elemental nitrogen with elemental oxygen and produces NO2 as the sole product. All right. Now this equation isn't balanced, and if we were balancing this reaction like normal, we would recognize that we have 2 nitrogen on the reactant side and only 1 on the product side. So we would multiply NO2 by 2, and then we would balance oxygen by multiplying oxygen by 2. Now this would be the balanced chemical equation. However, the thing to pay attention to here is in the definition of formation reaction, it forms 1 mole of product. So this stoichiometric coefficient must be 1 in a formation reaction. All right, it must be a 1 in the formation reaction. To make that coefficient 1, we need to multiply our entire reaction by 1/2. When we do this, we get 1/2 N2 plus O2 produces NO2. All right, and again, just to be emphatic here, I'm going to write in the 1s for the stoichiometric coefficient. So this is the balanced chemical equation for the formation reaction. Again, it satisfies the definition of formation reaction because we have only elements on the reactant side and we only have 1 mole of product being formed. So this here is the answer we're looking for, and the correct choice would be B for this problem. All right. Because the standard enthalpy of formation is equal to the change in enthalpy for this reaction. So hopefully that makes sense. All right. So there's the first problem from the ACS. We have another problem, which is number, oops. Let's open a new slide. Problem 18 from page, let's see what is this? Page 51. And again, this is from the first edition. So problem 18 asks, what is the value of the change in enthalpy for this reaction? So they give us a reaction, and that is H2, 3H2, 3 moles of hydrogen gas, plus, 1 mole of ozone gas. So that is O3. I had to look close to see if it was O2 or O3. Produces 3 moles of water, not water vapor, of liquid water. Phases are important for Hess's Law problems. And this problem asks us to determine the delta H change in enthalpy for this reaction. All right. And we're given 2 reactions. We're told that H2 as a gas reacting with 1/2 of a mole of O2, also a gas, produces 1 mole of H2O. And we're told that the delta H of this reaction is negative 286 kilojoules per mole. And then we're given a second reaction where actually I'm going to scoot this over just a bit. 3 moles of oxygen gas produces 2 moles of ozone gas, and the delta H for this reaction is positive 271 kilojoules per mole. All right. Okay, so this is a classic Hess's Law problem. And what we need to do, again, is we need to find, I'm going to call this reactant H2 is number 1. I'm going to call ozone number 2. Oh, wait, hang on. I'm in the wrong layer. I'm going to call H2 1, ozone 2, and H2O 3. We need to find these 3 components in the given reactions and manipulate those given reactions so that our desired reactants and products are on the desired side of the reaction with the correct stoichiometric coefficients. So first off, I am going to find number 1, which is which is hydrogen. All right. You'll notice that hydrogen is already on the reactant side, but it has the wrong stoichiometric coefficient. So I need to take this reaction there we go. So I need to take that first reaction, which is H2 gas plus 1/2 O2 produces liquid water. This is a delta H of negative 286 kilojoules per mole. I need to take this reaction and I need to multiply it by 3 so that H2 has the correct and H2O have the correct stoichiometric coefficients. And whenever you multiply your balanced chemical equation by a number, you multiply your value for delta H by the same number. All right, so this gives us 3H2 plus 3/2 O2 produces 3 moles of H2O. And the delta H for this reaction is 286, negative 286 times 3. So that's negative 856 kilojoules per mole. All right. So that is, I'm going to store that reaction away. So 3H2 plus 3 halves O2, producing 3 moles of water. It has a delta H of negative 858 kilojoules per mole. All right. Now looking back at our reaction, so we have our hydrogen and water figured out, but we need to get our ozone in the right place, all right? And ozone is in the second reaction, but it's on the wrong side. Oh, sorry, that's not number 3, that's number 2. It's on the wrong side of the reaction, and it has the wrong stoichiometric coefficient. So we're going to need to do a couple manipulations here to get ozone in the right place. So now, I'm going to zero that out for a minute. So, where are we? Okay, the reaction for ozone. The first problem here with the reaction for ozone, so we have 3 moles of O2 producing 2 moles of O3, which is ozone. This is a delta H of 271 kilojoules per mole. All right, and the first thing we need to do is we need to switch our reactants with our products because we need ozone on the reactant side. When you do that, you have to multiply your delta H by -1. So the first manipulation we're going to undergo for this reaction swaps. So now we have 2 moles of ozone producing 3 moles of O2, and the delta H for this reaction is negative 271 kilojoules per mole. All right, and then the second thing we need to do is we need 1 mole of ozone on the reactant side, not 2. So we are going to have to multiply the entire expression by 1/2. We'll also have to multiply our delta H by the same number. So this gives us 1 mole of ozone producing 3 halves of a mole of O2, and the delta H for this reaction is 1/2 of 271. So 271 divided by 2, or negative 271, excuse me, is negative 135.5 kilojoules per mole. I'm going to wait to round till the end, but I know that I can only have 3 sig figs in this number, so I'm going to put 3 lines there to remind me that this delta H only has 3 significant figures. And now I'm going to add this equation to this page. So we have now 1 mole of ozone gas producing 3 halves of a mole of O2, and the delta H here is negative 135.5 kilojoules per mole. And again, sig figs here for this delta H, we only have 3. All right, now that we have placed our 2 reactants and our product on the correct side with the correct stoichiometric coefficients we're ready to add, and you'll notice that on the reactant side of our second reaction, we have 3/2 mole, 3/2, 1.5 moles of oxygen, and we have the same quantity on the product side of the second reaction. So these two cancel each other, leaving us with a reaction where 3 moles, oops, not of H3 gas, 3 moles of H2 gas react with 1 mole of ozone to produce 3 moles of liquid water. And the delta H for this reaction is going to be the change in enthalpy of our two reactions added together. So negative 135 minus 858 is negative 993.5. But remember, we just did an addition. We're going to need to round to the ones place because both of these numbers are precise to the ones place. So the final answer after rounding with the correct sig figs and the correct units will be negative 994 kilojoules per mole. All right, and this is the change in enthalpy for this reaction. And when we look at our possible answers, the correct answer is D. All right, so that is that problem. All right. Now moving on to the third and final question, and if there are no other questions coming in through email or in my Canvas inbox, this will be the end unless you guys want to ask some live questions as well. But the third and final ACS homework question is problem 20 from page 52. Problem 20 from page 52. And this question says, use the given heats of formation to calculate the enthalpy change for the following reaction. So we're given a reaction here. That reaction is, let's see, here we go. It's B2O3. There's a solid plus 3COCl2. This is a gas. And it produces 2 molecules of boron trichloride, also a gas, and 3 molecules of carbon dioxide gas. All right, so now here they said use the given the given heats of formation. That's another way of saying delta H, change in enthalpy of formation. All right, and the way you use the, so they give us those values, the delta H of formation for each of the following are, so for B2O3, diboron trioxide, it's negative 1272.8. For carbon monoxide dichloride, which is not its real name, but you know, it's all we can name it for now. It's negative 218.8. All of these are kilojoules per mole. For boron trichloride, where are we? It's negative 403.8 kilojoules per mole. And then for carbon dioxide, it's negative 393.5 kilojoules per mole. All right, and the way you work these problems is it's always, remember, delta H. If we're talking about delta H, delta is always final minus initial, right? The final state is you add up all the delta H's of your products, final, minus all the delta H of formations of your reactants. All right, so all we have to do here is final minus initial, products minus reactants. Now, for the one thing you have to keep in mind when you're doing this, so let's do our products first, is the definition of change in enthalpy of formation, or heat of formation as they're called in this problem, is that 1 mole of that substance is formed. So if 1 mole of, for example, boron trichloride is formed, 403.8 kilojoules of energy will be released. However, in this reaction, we're not forming 1 mole of boron trichloride, we're forming 2 moles. So we need to multiply that heat of formation by 2. Likewise, if 1 mole of carbon dioxide was being formed, 393.5 kilojoules of energy would be released. But we're not forming 1 mole of CO2, we're forming 3. All right? So, oops. Let me get my black marker back. So we have 403.8 times 2. So this would be negative 807.6 kilojoules per mole. And then 3 times negative 393.5. This would be, let's see, minus 1180.5 kilojoules per mole. All right. Now, something to keep in mind is, as written, the significant figures for both of these are correct, and here's the reason why. You may be looking at the first one and going, yeah, you started with 4, you ended with 4, that's fine. But with the second one, you're like, wait, you started with 4, you ended with 5. The thing to remember is this 3 is exact. And so if you're multiplying 393.5 times 3, that's literally saying 393.5 plus 393.5 plus 393.5. So since you're doing an addition, you've got to have the same precision, so we're keeping the same decimal place for both of these. All right. Now, the first part of this problem, the heat of formation of our products, is the sum of these two numbers. And when we add them together, we get negative 1,988.1 kilojoules per mole. All right, that's not our answer. That is the delta H of our product. So this right here is just this. We still need to calculate the delta H of reactants, but I'm going to need to bump to a new slide. All right, so looking at the delta H for our formation of our reactants, this equals, so first reactant is B2O3, so that is 1 mole of diboron trioxide releases negative 1,272 72.8 kilojoules per mole. And again, because because this is the heat of formation of 1 mole, but in this reaction we actually are only dealing with 1 mole, so we don't have to multiply this by anything. All right, plus we have our second reactant, the formation of 1 mole of COCl2 will release 218.8 kilojoules per mole. But here, we don't have 1 mole, we have 3, so we need to multiply this by 3. So this will be negative 1272.8 kilojoules per mole minus, let's see, 218.8 times 3 is negative 656.4 kilojoules per mole. And when we take the sum of these two numbers, we get negative 1929.2 kilojoules per mole for the sum of the heat of formation of our reactants. All right, now the delta H of our reaction is products minus reactants, right? Oops. Let me just write this out to be complete. Oh, goodness. Tripping all over myself here. All right, there's reactants. So now, let's see, I'm going to dial back. There we go. All right, so our delta H, the sum of the delta H of formations, heat of formations of our products is negative 1988.1 kilojoules per mole minus the sum of the heats of formation for reactants, which is negative 1929.2 kilojoules per mole. This double negative will make a positive, so we end up with negative 1988.1 plus 1929.2, giving us a change in enthalpy for this reaction of negative 58.9 kilojoules per mole. And again, we just did a sum. Both of the numbers that we added are precise to the first decimal place. Our answer is precise to the first decimal place, so no rounding is required. So that is our solution. And when you look at the possible answers we have to choose from, the correct answer here would be C. All right, so that is the solution to the third and final ACS question. Alrighty. So at this moment in time, we are live and open for more questions. Let me just check through the email to see if we had any latecomers. Ooh. Let's see. Alrighty. Well, at this moment in time, it doesn't look like there's any more questions coming in. If that's the case, then we'll go ahead and conclude our live stream here. Another reminder before we go, and again, I'm totally interruptible. You can totally lob a question at me up until the last second. We'll totally get into it. But a reminder that exam 2 and the ACS the ACS homework homeworks 5 and 6 are all going down on Tuesday instead of Monday. So I bumped them a day. So they will both be going down on March 31st. All right. I'll be posting to Canvas a little bit later today. I've been grinding away at getting... again, my primary focus has been getting the multiple choice question quiz for multiple choice question quiz for Canvas up and running. So I'm building the problem bank using the combination math that we all learned in middle school, and so there'll be, based on the problem bank size, for each concept, there will be 56 different versions of it that can pop out. So everybody should be getting a unique set of problems. Oh, okay, question. Diana, can we do an exam caliber gas law problem? Yes, we totally can. Let me pull one up. Let's see. Okay, sweet. Here, let me grab one. Let's go to the Google Drive. Let's see. Let's go past sessions. All right, so how about an exam caliber gas law problem? Let's see. Yeah. Let's see. Okay. Sure. Here's a totally here's a totally exam caliber gas law problem. So I'm gonna write this up on the screen. Sorry, this is coming to me from. This is one that was used in ancient times. I wrote this problem about three-ish years ago, which was before I switched from Windows to Mac. Or no, I switched from Mac to Windows. It's opposite of the normal thing. Let's see. Also love an exam caliber redox reaction with half reaction method. We can totally do that. Diana, we can totally hit both of those both of those requests can be fulfilled. First, we'll hit the gas law one. So this is a problem that I wrote when I was a Mac user. I still am low-key a Mac user, but I'm currently using Windows, and so I can't just copy and paste the situation because for reasons that I find hard to fathom now, I was using Pages at the time. Okay, so here is an exam caliber gas law problem. One that was actually featured on a very real exam 2 that I gave back in 2017. So sulfur trioxide gas decomposes into sulfur dioxide gas and oxygen gas at 25.00 degrees Celsius in a 10.00 liter cylinder. Let's see, how many parts did I put in this problem? Just 2. Okay, part A is write a balanced chemical equation for this reaction. Part B goes like this. After the sulfur trioxide completely decomposes. After it completely decomposes, the pressure inside the cylinder kind of crunch there. The pressure inside the cylinder is 0.998 atmospheres. Determine the partial pressure of each gas after the reaction is complete if there are twice as many moles of sulfur dioxide as twice as many moles of sulfur dioxide than oxygen. Period. Wow. Okay, that is a full slide. Okay, so here is a totally exam caliber problem. So let's go ahead and dive in. All right, so first we need to write a balanced chemical equation for this reaction, and which means we need to take the names of our reactants and products and write them out. So first we're dealing with sulfur trioxide gas. This is a covalent compound, so this is 1 sulfur, 3 oxygen, and we're told it decomposes into O2 gas plus SO2 gas. All right. So those are reactants and our products. Now we need to balance. So we have sulfur and oxygen on both sides of this equation. The reactant side, 1 sulfur, 3 oxygen. On the product side, 1 sulfur, and we have 2 oxygen from O2 plus another 2 coming from SO2. And one thing you'll notice is sulfur is already balanced, all right? Sulfur is already balanced. We need to balance oxygen, and you'll notice we have O2 here, so it's all alone. It's isolated, right? So what we're looking for here, we've got 3 oxygen on our reactant side. We have 2 plus 2 on our product side. We want to multiply O2 by some number so that the number of oxygen on both sides of this equation are equal. And so what we need to do now is solve for n. Oh, hang on 1 second. One. Sorry about that. I had to take that phone call. It was my wife who's at work today, and she's a nurse with Kaiser, so she gets the fun of still being able to go into work and take care of patients who have the COVID. So, anyways, she was calling, so I just wanted to take it in case there was an emergency, but there's not. She was just on her lunch break. She's like, "Oh my gosh, I'm so sorry, I forgot you were streaming." So anyways, where were we? Okay, right. We need a number that we can multiply oxygen by to make the number of oxygens on both the reactants and product sides equal. So we're going to first subtract 2 from both sides, so we get 3 is equal to 2. Sorry, 3 minus 2 is not 3. We get 1 is equal to 2 times n. And then we divide both sides by 2. The number we need to multiply by is 1/2. And when we do that, you'll notice, whoa! You'll notice Photoshop doing weird stuff. Okay. When you multiply O2 by 1/2, now you have 1/2 times the 2 oxygens coming from O2. So this now equals 1 plus 2, and now our what's the word I'm looking for? Our atoms are balanced. However, just as we know, you can't leave a fraction in a balanced chemical equation. They have to be integers, right? The only time we see those fractions are when we're dealing with change in enthalpy of formation reactions. So we have to get rid of that denominator by multiplying the entire chemical equation by 2. And when we do that, we get 2 moles of SO3 plus 1 mole of produce 1 mole of O2 and 2 moles of SO2. So this is part A is done. Our balanced chemical equation. We scored the points, which is great. All right, now part B. Part B. All right, part B is, okay, so after the sulfur trioxide decomposes completely, the pressure inside this is, okay, so we have the whole part B, right? This is great exam practice because we've never done a problem like this before, right? And it turns out it's also great exam practice because this was on an exam at one point, okay? And so if you find yourself overwhelmed by the information and scratching your head going, I don't even know where to start, look back at the original problem. All right. Whoa, that's ugly. Let's look back at the original problem and ask yourself, what are you trying to find? All right. What are you trying to find? And it's hidden right here. Oops. Right here. We're told determine the partial pressure of each gas after the reaction is complete. All right. Now, that is what we're after. This is what we're trying to find. So we are trying to find the partial pressure of each gas. We want to know the partial pressure of O2 and the partial pressure of SO2. All right, that's what we're after. Now, let's write out what we're given. All right? Let's take a look at what we're given in this problem. All right? The first 2 bits of information that we're given come from the very beginning of the problem. We're told that this reaction happens, that it decomposes, sulfur trioxide decomposes at a temperature of 25.00 degrees Celsius. All right? So that's one piece of information. We're also told the volume of the cylinder in which this reaction happens is 10 liters. All right, so those are 2 given pieces of information. All right, now, sorry, hang on. Oh, it's texting me. Let's see. I'm sorry, hang on. Okay. All right, so we have those first 2 pieces of information. Now let's look at for any additional information given in part B. So we're told that it decomposes completely. The sulfur trioxide does, so there's no sulfur trioxide left. We're also told the pressure inside the cylinder. All right, now this is the total pressure. All right, because it's the pressure inside the cylinder. What's inside the cylinder? Both of these 2 gases, oxygen and sulfur dioxide. So our total pressure is equal to 0.998 atmospheres. All right, and then the last piece of information, well, actually, before we go there, so we've been told the total pressure, and the total pressure is part of an equation, an algebraic equation. So one tip-off is total pressure. The second is we're asked to find partial pressures, right? So this should be kind of triggering something in your brain. Hopefully you'll recall that I recall me saying in lecture that I'll be testing on 3 gas laws: the combined gas law, the ideal gas law, and Dalton's law of partial pressures. And so when you hear me ask you to determine the partial pressures, you should think, okay, Dalton's law. There's an algebraic expression. I should write that out. Total pressure is equal to the partial pressure of O2 plus the partial pressure of SO2. All right? That's because the total pressure of a mixture of gases will always be equal to the individual partial pressures of each component of that mixture. And one thing you'll notice is these are the two quantities that we're trying to find. So this equation is gold, all right? This equation is going to lead us to the answer. We just need to figure out how to get there. Now, there's one last piece of information given. We're asked to determine the partial pressures if there are twice as many moles of sulfur dioxide than oxygen, all right? So we're told something. We're told that we have, I'm going to put this in quotes, we're given that we have twice as many moles of sulfur dioxide as oxygen. All right, what does that mean? That means we have 2 times the number, that the number of moles of sulfur dioxide is double the moles of oxygen. And we can write this as an equation, right? Moles, our moles of SO2 are equal to 2 times the moles of O2. All right. So this is all of our given information. All right, explicitly given information. There's one last piece of data, of info, that we'll need to solve this problem. All right, you'll notice that here we're being asked to find pressures, right? We're given volume, we're given temperature, and we're told something about moles. Now, whenever you're dealing with moles, temperature, volume, that makes me think of the ideal gas law, PV equals nRT. All right, that's what relates all of these constants together. And here we can actually write out specialized or a custom ideal gas law for each gas. We could talk about the pressure of SO2 times the volume is equal to moles of SO2 times RT. And we could also talk about the pressure of O2 times its volume is equal to the moles of O2 times RT. Now we can isolate, we can do an algebraic kind of rearrangement. If we take the ideal gas law, divide both sides by volume, we can isolate pressure on one side of the expression. The pressure of a gas is equal to the moles of that gas times the ideal gas law times the temperature divided by the volume. And the reason why this is useful is because here we can now substitute in for pressure of O2 and pressure of SO2. All right? Now hang with me for a second. What's on this slide? Oh. All right. So if we take the expression that our total pressure is equal to the pressure of SO2 plus the pressure of O2, and we substitute in the expression we just derived, that the pressure of a gas is equal to the moles over R times T times, divided by V, we can substitute in the total pressure is equal to the moles of SO2 times RT over V plus the moles of O2 times RT over V. All right. And you'll notice here that we have a common factor in these two quantities we're adding. We have an RT times V. If we factor this, we get total pressure is equal to RT over V times moles of SO2 plus moles of O2. Finally, you'll remember that expression that we wrote. Oops. Where moles of SO2 was equal to 2 times the moles of O2. If we take this expression and substitute in, we get an expression total pressure is equal to RT over V. Oops. Times 2 moles of O2 plus 1 mole of O2 which is simply total pressure is equal to RT over V times 3 moles of oxygen. All right, now why did we do all this? We did all this because when you look at our given information, okay, so when you look at our given information, we have total pressure. We know R, it's always constant. We're given temperature and volume, so we can solve for moles of O2. Okay, Diana, you've got a question. Do you have the twice as many moles bit equation written backwards? Okay, so actually no, because we have twice as many moles of SO2, so there's double. That means we have to multiply the moles of O2 to make them equal. Yeah, totally. All right. With this equation, we can solve for our moles of O2, and the reason why that is important is once we know the moles of O2, we can solve for the partial pressure of O2, right? So let's get at this. Actually, I need to scoot this over just a little bit. Hooray for lasso tools. So we need, let's see, I'll need to scoot this over a little bit too. If you can hear the rustling of leaves, there's this big, beautiful tree outside my office window, and the window's open, and the wind is wafting through it gently. So if it sounds like I'm podcasting from outside, it's almost actually the case. Podcasting, live streaming, whatever. I think it's cooler to say I'm podcasting, but you know, okay. So we need to isolate moles of O2 on one side of this reaction. Oops. So we are going to multiply both sides by V over 3RT. V over 3RT. When we do, 3 cancels, RT cancels, V cancels. We get moles of O2 are equal to volume times total pressure over 3RT, and we know all of these quantities. Our volume is 10 liters. Our total pressure is 0.998 atmospheres. 3 is 3. R is 0.08206 liter atmospheres per mole Kelvin. And then temperature, you'll notice that the temperature we were given is in degrees Celsius, all right? And we need it to cancel with Kelvin, so we actually need to convert degrees Celsius to Kelvin. And when you do, plus 273.15, you add 273.15 to our degree C, and that gives us 298.15 Kelvin. All right, so now all of our units cancel. Kelvin cancels Kelvin, atmospheres cancel atmospheres. Oh wait, no. Moles don't cancel because we're solving for moles, but liters do cancel liters. Okay. All right, here's the deal. Okay, hang on one second. Alrighty. Okay, so alright, so we are now crunching our numbers, solving for moles of O2. So we have 10 liters times 0.998 divided by 3 divided by 0.08206 divided by 298.15. All right, this gives us 0.1359, I'll call it 97 moles of oxygen. When you look at the number of sig figs we can keep, we can hang on to 3 because our total pressure has 3 significant figures. So our value for moles only has 3 sig figs. Now that we know how many moles of O2 we have inside this mixture, we can get a value for the partial pressure of oxygen by multiplying 0.13597 moles times the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin, times our temperature, 298.15 K, divided by our volume, which is 10 liters. Units wise, moles cancel, volume cancels, and temperature cancels, leaving us with pressure in atmospheres. So we have our moles of O2 times 0.08206 times 298.15 divided by 10. All right, and remembering that we only have 3 sig figs in our value for moles, we get a final answer of our partial pressure of O2 is 0.0333 atmospheres. All right, now that is a Herculean effort. We've made it. We've done a ton of math, a ton of algebra, a ton of problem solving. It's really easy to feel like you're done when you finally get a value. But it's important to look back at that thing that we wrote when we started working this problem, what we're trying to find, to make sure that we actually did. And we found part of it. We were asked to find the partial pressure of each mixture, or of oxygen and sulfur dioxide. Right now we only have the partial pressure of oxygen. However, we're very close to the end, because Dalton's law of partial pressures, total pressure of the mixture is equal to the partial pressure of SO2 plus the partial pressure of O2. At this moment in time, we know both the total pressure and the partial pressure of oxygen, so we simply need to isolate the pressure of SO2 on one side of this expression. So the partial pressure of sulfur dioxide will be equal to our total pressure minus the partial pressure of O2. Total pressure is 0.998 atmospheres. Partial pressure of oxygen is 0.333 atmospheres. And so our partial pressure of SO2 will be the difference between these two numbers, which is 0.998 minus 0.333 is 0.665 ATM. So these are the two partial pressures of the mixture of gas produced by this reaction. And that took a mighty swing. That was an exam caliber problem. Okay, Raj, you asked a question about pressure a while ago. Yes. So your question was, will I ever give pressure a pressure in millimeter of mercury? I totally could. So if you look at pressure units, there's so many to choose from. Pressure units, atmosphere is the standard one, the metric one, but there's also torr is very common, millimeters of mercury, kilopascals, and more. Right? Since these exams are going to be open book, it could be given to you in any sort of pressure units can come at you, because you don't have to memorize any of them, right? You just have to look them up. Okay, follow-up question. Is there a way to do it through the mole fraction? Oh, do this problem through the mole fraction. So you're saying do it through, because there's two ways to write Dalton's law of partial pressures, right? So you can write Dalton's, okay, here, hang on one sec. Okay. Sorry about that. It's okay. So right. So there are two, Raj, your question is, there are two formulations of Dalton's law of partial pressures. The first being, and this is the one that I used for this problem, the total pressure of a mixture of gases is equal to the mixture of each component out to the nth, whatever the last one is. That's one way to formulate it. The second way to formulate Dalton's law of partial pressures is like this. The partial pressure of a gas is equal to the mole fraction of that gas times the total pressure of the mixture. And the mole fraction, and that's a capital chi, which is a Greek letter, is equal to the moles of that individual gas plus the total moles present in the mixture. And the quick answer to your question, Vraj, is yes. You could totally solve this using this formulation of Dalton's law of partial pressure. The way you do it is you'd come at it like this. The mole fraction of oxygen is equal to the moles of oxygen divided by the total moles, right? Which is moles of O2 plus moles of SO2. Then you can use the expression that we wrote that moles of SO2, because we know they're twice as many, is equal to 2 times the moles of O2. You can use this to substitute in here, and that would give you the mole fraction of oxygen. Then you could solve for it. Actually, looking at it this way, it's probably faster and easier to use this formulation of Dalton's law of partial pressures to solve this problem. But if you do it, it'll come out the same. So the answer to the question is yes. You could use either formulation of Dalton's law. I kind of tend to think of the first one, the one that I wrote out first, more prominently, but the second one gets the job done just as well, and in this case, maybe even better. Okay, hang on. A couple other questions. Let's see. So, will this be a multiple choice question? Okay, so would the question that I just wrote out and did be a multiple choice question? And the answer is no. The problem that I just solved would be on the take-home part of the exam. The multiple choice questions aren't designed to be long, because they're designed to be short, quick, similar to maybe the ACS homework or the easier homework problems in the TRO textbook. So I would, if you're wondering what are the multiple choice questions like, this would be on the take-home exam. It's a lot of algebra, a lot of steps, and you're not going to have a lot of time per problem on the multiple choice, so they're shorter by design. If you're looking for kind of inspiration, or what to expect, kind of, you know how in the back of the chapter, at the end of the chapter in the TRO textbook, there are homework problems, practice problems, and how the problems in there kind of start easy, and then the deeper you get into them, the harder they get. The multiple choice questions are going to be similar to the easy questions you run into in the textbook. Hopefully that answers your question. Alrighty. Okay. So, okay, Diana, you also wanted to see a half reaction problem that would be exam caliber. So let's take a stab at one of those, because on the take-home exam there is going to be a redox reaction where you will have to use the half reaction method to balance a chemical equation. So let's take a look. Take a look at that situation. And for inspiration, I will go. Let's see. Yep. Straight to a redox problem that made it onto a second exam. So for the following redox reaction, the reaction between chloride ions and chlorite ions, producing chlorine. All right, we're asked to determine the oxidation state of each element, and identify the oxidizing agent and reducing agent, and then we're asked to balance this chemical equation using the half reaction method. So first off, so for our oxidation states, the chlorine in chloride has an oxidation state of -1. Doing the easy ones first, the chlorine in chlorine has an oxidation state of 0. Now, when you look at chlorine and oxygen in chlorite, we know that the more electronegative element in the compound will take its regular ionic charge. So oxygen has an oxidation state of -2. And chlorine then will have to have an oxidation state of +3, because we know that our total charge on the species is -1. We have 2 oxygens with oxidation states of -2. So if our total negative charge is -4 and our net charge is -1, chlorine has to be a +3 to cancel all but the last, or to balance with all of the last, but the last negative charge. So those are our oxidation states. Now, when it comes to oxidizing and reducing agents, one thing you can see is that chlorine starts at -1 in chloride and ends at 0, which means that chloride is, let's see, -1 to 0. That means it's lost electrons, it's oxidized. All right. The compound that causes that oxidation to happen is chlorite. So ClO2 is the oxidizing agent. Now, when you look at the chlorine in chloride, it starts at +3, it ends at 0. So you've gone from a +3 to a 0. That means you've gained electrons. So it's been reduced. The species that reacts with this chlorine, causing the reduction to happen, is chloride, Cl-. So chloride is the reducing agent, chlorite is the oxidizing agent, and that is the first part of the problem. The second part of the problem, we need to use the half reaction method to balance this chemical equation, chemical reaction that takes place in acidic media. So the first step of the half reaction method is we need to split our reactants up, all right, into the oxidation half reaction and reduction half reaction. So first off, we have chlorite becoming chlorine, and then we have chloride becoming chlorine. All right. To balance our the reaction of chloride and chlorine together, first we got to balance our atoms. So we need 2 chlorines on our reactant side. Then we need to balance our charges, and we have a -2 on our reactant side and a 0 on our product side. And remember, you can only use electrons to balance charges. So by adding 2 electrons to the product side, our charges are now the same on both sides of this reaction. So that is the first half reaction. So Raj, in basic media, so you'll still use water to balance oxygen, and actually to balance in basic media, you will still use H+ hydronium to balance the hydrogen, but after adding the H+, for every molecule of H+ you add, you add an additional OH. So the OH and the H plus neutralize each other. But because I didn't spend time on this in lecture, you're guaranteed to get one in acidic media. I won't give you one with basic media, just because we had to axe that due to the fact that we were running a little bit behind schedule. So you won't have to worry about basic for the second exam. All right, now looking at our other half reaction. So we need to balance our atoms. This is going to be a little more intense or involved, I guess I should say. We have chlorine and oxygen, 1 and 2. And on the product side, we just have chlorine. So first step, to balance our chlorine, we're going to multiply multiply chlorite by 2, giving us 2 chlorines and 4 oxygens. Now, whenever you need to balance oxygen, you always add water. So adding 4 molecules of H2O will balance the number of not 0, there's 4. It'll balance the number of oxygens, but it also introduces 8 hydrogen to this reaction. To balance hydrogen back on the product side, we're going to add hydronium ions. Let's see, that's a little hard to see. So 8 H pluses, and now our atoms are balanced for the chlorite half reaction. All right, atoms are balanced. Now let's take a look at our charges. So for our charges, we have a positive 8 coming from our hydronium, and we have negative 2 coming from chlorite, for a total charge of positive 6. And then that's the reactant side. On the product side, chlorine doesn't have a charge, hydrogen doesn't have a charge. So this is the charge situation we need to balance. Now we have a positive 6 on our reactant side, which means we need to add 6 negative charges. And when we do, we have negative 6 plus 8 minus 2 is equal to 0. And now the charges are balanced on both sides of our second half reaction. Ooh. Hang on, it looks like our stream something's happening with our stream. Let's see, Wi-Fi's connected. Stand by. Let's see. All right, hang on one sec. We're having some technical difficulties here. I might have to end this stream prematurely and then oh gosh. Oh, let's see. Oh, it says we're live now. Okay. Oh gosh. Like things are back. Let me just double check really quick. I apologize if watching this if you didn't experience any problems during the stream. All of a sudden it was like shutting down and I wasn't getting feedback. Okay. Okay, hang on. Okay, it looks like we're good. So I'm just gonna keep rolling. Okay, my apologies for that mix up. Okay. So let's get back to the problem. Okay, so as of right now, we have our atoms and our charges balanced for both of these reactions. However, before we can recombine them, we need to make sure that our number of electrons are equal, that the number of electrons consumed are equal by one half reaction equal the number of electrons produced by the other. And to do that, we need to multiply our chloride half reaction by 3. So this will change things to 6 chlorides becoming 3 chlorines and producing 6 electrons. All right, and now that we are producing the same number of electrons that are being consumed, we're ready to recombine these two together into a balanced chemical equation. So taking our two half reactions then. So we have oh goodness. What's screaming at me? Okay, everything's fine. Okay. So our two half reactions, where we have 6 electrons reacting with 8 hydronium ions plus 2 molecules of chlorite, producing chlorine plus 4 molecules of water. That's one half reaction, and our second half reaction involves 6 chloride ions producing 3 chlorine and sorry, I forgot to write this on the previous page, and 6 electrons. That's the whole point. Now when we add these two half reactions together, we did our job. We did our job well, because 6 electrons will cancel 6 electrons. You should never have any electrons left over. And the final balanced redox reaction will have 8 hydronium ions plus 2 chlorite ions plus 6 chloride ions plus, okay, now here you'll notice we have 1, that's fine, 1 chlorine plus 3 chlorines, so that adds to 4 chlorine molecules plus 4 water molecules. Now, looking at this balanced chemical equation, it is balanced, but it's not our final answer. It's not our final answer because every stoichiometric coefficient here has a common factor of 2. All right? There's a common factor of 2 in each one of these dudes. So we need to factor that, because a balanced chemical equation has the simplest whole number ratio between reactants and products. So the final answer will be 4 hydronium ions plus 1 molecule of chlorite plus 3 chloride ions will produce 2 molecules of chlorine and 2 molecules of H2O. All right, so this is the final answer for the balanced chemical equation the final balanced chemical equation for the redox reaction we were given in this example. Cool. Alrighty. So that is that. Are there any additional questions before we close down today's? All right, it reconnected. Sorry, we're having some streaming issues here. Alrighty, if there are no further questions. Oh wait, here we go. We're getting some popping up. Okay. So when is my 420 stream? Oh, hang on. Wednesdays. So I'm also doing you'll see popping up on this channel. I'm doing some streams to support my OChem lab. Let's see. So those streams, which will be OChem focused, just like this is your time, which is Gen Chem focused. Those streams will be going on Wednesdays. There's a possibility that I'll be doing it this Monday as well. Same time. There we go. Alrighty, we have been, let's see, going at it for about an hour and a half. Totally. Thanks everybody for totally, my pleasure. Thanks for popping in. Great questions. Hopefully they'll be helpful. I'm gonna go back into my cave and keep plugging away on my multiple choice question problem bank. Writing this thing is taking a ton of time, as I already said earlier, because it's not writing one test, it's writing like Tuesday will be the exam. So totally my pleasure. I totally I get excited when this is effective for you guys. So thank you for logging in, and I will catch you on the flip side of this weekend. Bye.